Good evening, Sunny Bunani, goeienaand, doe my lang. My name is Kinta Burger, I'm the Registrar of UJ, and it's my honor and privilege to welcome you on behalf of the Vice-Chancellor and the University to the Professorial Inauguration of Professor Penny Govender. A warm welcome to all of you, the family, friends and colleagues of Prof. Penny, to this joyful and landmark event. In particular, I welcome Professor Deborah Meyer, the Executive Dean of the Faculty of Science, and our respondent this evening, Professor Robert Gengan, from the Durban University of Technology. Welcome to you, Professor. Also, a warm welcome to all members of Senate and other colleagues and guests of Professor Govender, who are joining us via our online platforms. Ladies and gentlemen, the inauguration of professors is a public ceremony in which a newly appointed professor is inducted into office and deliver their inaugural address. The ceremony of the inauguration of professors has its roots in the medieval university and serves multiple purposes. Firstly, it's an expression of welcome and an entry for new professors joining the circle of colleagues who are already professors. Secondly, it provides a platform for the professors to display their expertise in the discipline and showcase their research. And thirdly, it stands out as a moment of pride and celebration for the incumbent, the family, the fellow scholars, the university and society. In essence, it is a celebration on the achievement of major milestones, contributions to the discipline, and ultimately the impact on society. Today, ladies and gentlemen, we gather to witness the entry of Professor Govender to the illustrious community of scholars at the University of Johannesburg. This evening, we will listen to Professor Govender as one further step in the journey of being a professor. This is a journey which does not culminate once this lecture has been given. It is rather a self-reflective pause in the journey of the professor, with the promise of more to enrich our minds and simultaneously contributing to the rich intellectual body of work in the discipline. Prof. Govender, we are looking forward to your address, and I now invite the Executive Dean, Prof. Deborah Meyer, to introduce Professor Govender to you. I thank you. Riali Boga, Siyabonga, baie dankie.
Thank you, Professor Burger. Good evening to our viewers online and to the colleagues in the room. It is indeed a pleasure for me to introduce Professor Govender to you. Penny Govender was born in KwaZulu-Natal and is the youngest of 3 children in her family. She is also a first-generation scholar. Penny studied at the M.L. Sultan Technikon, which is now known as Durban University of Technology, for a National Diploma in Analytical Chemistry, up to a Master's in Technology Chemistry. She also managed to gain work experience as a laboratory assistant from 1995 to 1997 in the labs at the M. Sultan Technikon. Her first lecturing experience was gained at the University of the North in 1997, and she later on joined the Durban University of Technology as a lecturer. From 1998, in 1999, she took a gap year and spent time in the UK for 12 months, and later on, from 2000 to 2002, returned to DUT as a contract lecturer. During that period, it was difficult to secure a permanent job as there were talks of merging institutions. So Penny ended up applying for a job in Johannesburg and found herself employed at the Technikon Witwatersrand as a permanent lecturer in July 2002. This means that Penny has now been at this institution for approximately 19 years and counting. When Penny joined TWR, she was completing her MTech at the time. While it was her intention to immediately pursue her PhD after graduating with the master's, but due to teaching loads, this became impossible. She made an attempt in 2007-2008 to register for a PhD, but unfortunately took ill with Bell's palsy and had to spend more than 6 months in recovery. In 2009, she successfully registered for a PhD at the University of the Witwatersrand under the supervision of Professor Marx and co-supervision of Dr. C.B. Perry. Penny graduated in 2013 and upon application was promoted to senior lecturer in the same year. Penny has always played an active role in her department and was in charge of many portfolios and serving as the acting Deputy Head of Department Teaching and Learning from September 2012 to March 2013, and subsequently as the actual Deputy Head of Department Teaching and Learning from April 2013 to March 2014. This served as a good foundation, and she later became the Head of Department for the Department of Applied Chemistry from July 2016 to December 2019. Since obtaining her PhD as an emerging researcher, she set up her Computational Chemistry research group, which gained momentum, and in 2017 and 2020, she was promoted to Associate Professor and Full Professor, respectively. To date, Penny has graduated 7 PhDs and 6 MSc students, supervised 5 PDRFs, and is currently supervising 3 PhD students and 1 postdoctoral fellow in her group. Her publication output is recorded at 93 papers to date, 4 book chapters and 1 book in print, and several presentations at conferences. She enjoys a Scopus and Google Scholar H-index of 18 and 21 respectively. Penny's research area is strategic, whereby she focuses on global challenges such as water, energy, and dreaded diseases. Her aim is to use quantum mechanics, density functional theory, to explore areas like water remediation, smart materials for energy storage and production, and molecular dynamics for finding ways to understand and target dreaded diseases for quick recovery solutions. On the other hand, she also believes in paying it forward and therefore continues to make her contributions to the wider scientific community by participating in duties such as mentorship, reviewing articles for journals and research organizations, and examining theses, amongst others. Penny has indeed earned her stripes and was the recipient of the 2017 Faculty of Science highest research output in the senior lecturer category, and in 2018 she received the Vice-Chancellor's Distinguished Award for Most Promising Young Researcher of the Year. So it's my pleasure to introduce to you Penny Govender.
Good afternoon, Acting Vice-Chancellor, Professor Berger, Executive Dean of the Faculty of Science, Professor Meyer, guests in the room today, guests and colleagues that have joined us online, welcome and thank you for attending today's lecture. So my lecture today is split into 2 parts. Firstly, we'll focus a little bit on the background on computational chemistry, followed by some selected highlights of our research to date. So, what is computational chemistry? It is a branch of chemistry that makes use of simulations to solve chemical problems or to answer research questions. It can be used in conjunction with experimental work, or it can be done solely, or work solely on computational work. This means we can use computational chemistry as a pre-tool, a post-tool, or a complementary tool to experimental work. What are some of the advantages of computational chemistry? It's actually a quick and easy way to troubleshoot experimental problems that we may have, and this in turn reduces the cost of chemical purchasing and so forth. It also promotes a greener form of chemistry because you save on buying unnecessary chemicals. Safety is of key importance, and we know that when you work with chemical compounds, there is some form of danger that is involved. So prior to actually doing experimental work, you can actually do some computational probing before you take your research into the lab environment. Some of the software that we use in computational chemistry, especially in our group, is Material Studio, Schrödinger, Gaussian, amongst many more that's available. And some of the calculations that you can do with this particular software is quantum mechanics calculations and molecular mechanics calculations. Very quickly, when you think about quantum and you think about electrons, these are some of the scholars that come to mind amongst Niels Bohr, Einstein, and Max Planck. From Dalton to Schrödinger, we were able to understand and unpack the behavior of molecules, atoms, and electrons. Heisenberg and Schrödinger were noted as fathers or forefathers of quantum mechanics, together with the likes of Slater, Hartree-Fock, Korn, and Pople, who came on board later on to assist in solving the Schrödinger equation. Moving from theory to digital, it would be remiss of us if we don't mention these three individuals. Seymour Cray, who was responsible for building the first supercomputer in 1975. Gordon Moore and Robert Noyce were co-founders of Intel. If you are using a computer that is not using an AMD processor, then it's most probably using an Intel processor. Intel stands for integrated electronics. So it's integrating the electronics of your computer. Thanks to their ingenuity, we've made leaps and bounds in the field of computational chemistry and, might I add, the 4IR space. In computational chemistry software, we make use of databases, and these databases include information from experimental work and computational work. It's the algorithms in these software that actually extract this input to help you solve your chemical problems or the research question that you want answered. There are also several methods, from quantum mechanics to molecular mechanics, that are embedded in your computational software. As you can see from this slide or from this graph that's presented to you, there is a compromise between the methods that you would choose, computational cost, and accuracy. Depending on what you actually want to achieve and the resources that you have available, this will direct you to exactly which method that you would want to use and save yourself some computational costs, but still have some form of accuracy when you're performing your computational calculations. So this takes us into molecular mechanics. Molecular mechanics makes use of classical mechanics or classical physics that actually makes use of Newton's second law of motion. What this simply means is bonds, angles, dihedral angles are actually treated as springs obeying the Hooke's law, whereas atoms are spheres with element-dependent mass. In molecular mechanics, we're not dealing with electrons, neither are we dealing with orbital interactions, because this is not an electronic structure method. When we're using or when we need to calculate potential energy of a system using molecular mechanics, these are some of the components that we will include in our calculation. The components include van der Waals interactions, distance distortion, dihedral distortion, Coulombic interaction, and angle distortion. On the right-hand side, you can see an animated diagram, and these are some of the output that you can achieve from your molecular mechanics calculation. Visibly, you can see what is actually happening there for the ammonia molecule is a stretching mode vibration. And this makes the research interesting because you can observe what is happening through your GUI systems. Molecular mechanics also make use of what we call force fields. So what are force fields? They are simply a collection of associated constants and functional forms. So you get different types of force fields for different types of molecular systems. For example, if you want to work with organic compounds, then you would have to use a force field like MM2, MM3 for that particular system. If you're looking to model biomolecules, then you would use something like AMBER or CHARM. Now, of course, this method will have its advantages and disadvantages. So the advantages of molecular mechanics is that you can use large molecules, or you can model large molecules. It's fast and it gives you good results for structures. It's also used as to model starting geometries for other methods of theory. The disadvantages is because it's not an electronic structure method, you cannot get any information about the reactions that take place, transition states, and so forth. Also, many of the compounds don't have any parameters. And of course, there will be no orbital information because this is not an electronic structure method. On the other hand, quantum mechanics is. So the three methods that fall under quantum mechanics is the Hartree-Fock model, semi-empirical model, and density functional theory. Ultimately, what are we trying to do in the electronic structure method? We're trying to solve the Schrödinger equation so that we can understand our molecular system at an atomistic level or at an electronic level. The Schrödinger equation was exactly solved for the hydrogen atom because it contains one electron. However, as soon as the number of electrons increases, so does the complexity of the calculation. So what we need to then do is make approximations so that we can solve the Schrödinger equation exactly. Some of the approximations include the Born-Oppenheimer approximation. What actually happens there? We assume that the nuclei don't move. Then you can even include Hartree-Fock approximation. Here you treat the electrons as separate motions. Finally, LCAO, linear combination of atomic orbitals approximation. What are we actually doing here? We get electron motions in molecules by combining electron motions in atoms. So we have our first quantum model, which is the Hartree-Fock model. This model arose when we made approximations to the Schrödinger equation. What the Hartree-Fock model, each electron moves in an average electric field produced by other electrons. Of course, this model also has advantages and disadvantages. The disadvantage is that the energy results that we obtain is generally inaccurate. However, the advantage is that the output from the Hartree-Fock model can actually be used as an input for the next level of theory. So this takes us to post-Hartree-Fock methods. The post-Hartree-Fock method is an improvement on the Hartree-Fock model. Why? Because it deals more explicitly with electron-electron interactions. So there are many models that fall under the post-Hartree-Fock model. I've put down two here. So the first one is configuration interaction, CI. So in this model, the wave function is improved by adding contributions from unoccupied orbitals. However, this particular method has an extreme computational cost, which is something that you don't want to have. The second one is the Moeller-Plesset perturbation theory. Here, we simplify the Hamiltonian, so exact wave functions and energies can be calculated. These values can in turn be used to estimate the wave functions and energies for the complete Hamiltonian. Yet again, it's computationally expensive to use this particular method. So you are still spoiled for choice because we have two other methods that you can choose and are considered to be an improvement on the Hartree-Fock models. The first method is semi-empirical. In this particular method, we ignore part of the Hamiltonian. Secondly, we replace some of the integrals with experimental data. Density functional theory, on the other hand, completely ignores wave function, and we only work with electron density. So a little bit more on semi-empirical methods. Here again, we also have different types of models because you would have different types of molecular systems. And depending on what molecular system you are working with, you would choose this particular model to be included in your simulations. So in the semi-empirical method, we only look at the valence electrons, and some of the integrals are neglected. In this particular method, what is nice about this method is a part of it comes from experimental data. So experimental results are used to parameterize integrals. Different methods are parameterized to reproduce different properties. Here we use minimal basis sets and we employ a non-iterative process, meaning non-stepwise. Here again we have advantages and disadvantages. The advantages of this particular method is that it's fast, it can handle large molecules, the parameters are available for solution phase modeling, and it gives you good qualitative results. On the other hand, the disadvantage is it's limited to ground state equilibrium geometries. You know, in chemistry, we also get excited state molecules. So this is one of the limitations. And the parameters are not available for all of the atoms. This takes us to density functional theory. Of course, it's an electronic method, and it's used to determine electron densities. Once you have the electron density of the molecule, you'll be able to see what the molecular properties are. It's a very attractive method since it deals with inter-electron interaction, called electron correlation. It makes use of functionals, and the electron density is a functional to determining the energy of that molecular system. So DFT contains no approximations. It is exact. And all we need to know is the exchange correlation energy as a function of the electron density. So DFT is a very popular method because it gives you a good balance between performance, accuracy, and computational cost. Within DFT, we have different classes of functionals. And this is what you see on the slide here. On the left-hand side, you can see a ladder format, moving from LDA, GGA, meta-GGA, hybrid, and double hybrid. So LDA stands for local density approximation. What does this actually do? It actually treats the system to have a uniform electron gas, irrespective on the amount of electrons that we are dealing with. GGA stands for generalized gradient approximation. This particular functional brings in a gradient correction factor so that the non-uniformity of the electron density is taken into consideration. The final class is the hybrid functional. The hybrid functional is actually a combination of the HF model and your DFT model, where approximations to the exchange energy plus electron correlation is taken into consideration. In the slide, you see a plethora of functionals that you can use. Here, we're only showing 200 benchmarked functionals, but there are more available. So what does this actually tell you? That you can model any system of your choosing. You are bound to find a functional that you can use in your input files that can be used to instruct and model that particular system according to what information you are looking for. In addition to a functional, you need to include what we call a basis set. What is a basis set? It's simply a mathematical description of the orbitals within a system. So you get minimal, you must have heard me say minimal basis set when we spoke about the HF model. Here you can see on the left-hand side, there's a large range of basis sets that is included in the slide. So the larger the basis set that you use, the more accurate the approximation of the orbital, since lesser restrictions is placed on the movement of the electrons in the system. Finally, if we had to make a comparison between HF and DFT, so DFT, in a nutshell, DFT is a theory that is exact, and the equations are solved approximately. In Hartree-Fock, the theory is approximate, and the equation is solved exactly. For our research work, we've been using DFT. Like I mentioned, it gives you good, accurate, progressive results. Moving on to the second part of the talk is we start off with our research strategy. So what we looked at, or what I looked at, before we even continued with our research, was to see what the global challenges we are facing in South Africa, in Africa, across the world. These are some of the topics that come into play. climate change, food security, water security, energy, health and welfare. So we've decided to go for the last three topics. Very quickly, this is my research group of present and past students that are focused on theoretical work, experimental work, and a combination of both theoretical and computational work. So we know we have a problem with water. We have heavily polluted waters. Lots of rural areas cannot access water, right? Our industries are polluting waters on a day-to-day basis, and we need to do something about this. So our first project focused on geochemical modeling, and we used the FreakC software. So what does this acronym stand for? FreakC, pH. pH, as you all know, measures alkalinity or acidity. RE stands for redox, because we have reduction oxidation reactions. EQ, equilibrium. And C actually stands for the language in which the software is written, C++. So what was our aim? So we wanted to build a hybrid database to include selected organic and inorganic pollutants present in the South African water system. This database would then be included in this FreakC software. And this is something that is allowed by the developers of FreakC. And we would use analytical methods such as ICP-MS, IES, HPLC, GC-TOF to get the experimental data that we can add into these databases. Ultimately, we want to develop a predictive tool that we can use for monitoring both organics and inorganic pollutants in the South African water system. So this takes us to the next slide. So what did we do? We actually generated an application, an Android app called, I don't know if you can see it very clearly, called Fate and Transport. So if you look at the little pictures there at the bottom of your screen, you can see when you access the app, the pages that it actually takes you through, right? So we could actually predict parameters such as fate and transport of metals and anions, solubility and saturated indices, and by simply inputting physicochemical data like your temperature, your pH, and concentration of your anions and metals. This is a primary or key example of showing you what machine learning is about. So for this particular project, even though we stopped here, we have intentions of adding more to the database so that we can predict different parameters along the way. Moving on to the second research project. So we focused on water remediation using the concept of photocatalysis. Now, photocatalysis is a wonderful field. This is what I realized, because you're using one natural resource, which is the sun, sunlight, to actually help another natural resource, which is water, right? So ideally, what do you want to do here? You want to generate a material that will absorb sunlight. So it needs to absorb in the visible range. When that happens, you're getting the movement of electrons from what we call, in your material, if you look at the schematic, from a valence band to a conduction band. When this happens, you're catalyzing a chemical reaction. You're pushing a chemical reaction to take place. This chemical reaction will then cause radicals or form radicals. The radicals then attack your pollutants in your water and degrades it to a less harmful form. So this is basically the concept of what photocatalysis is about. And it's already used in many industries. Like you can see the examples that I put there on the left-hand side. Air purification, degrading your VOCs, which is volatile organic compounds. Bacteria, breaking down bacteria. Fungus, deodorization, right? So these are the key things that photocatalysis is used in. So we wanted to get our feet wet regarding this field. So we did a little bit of experimental work first. So what we did is we looked at nanomaterials, and then we doped these nanomaterials with transition metals. And we did a comparison to see what happened to these new materials that we formed. So of course, the photocatalytic activity increased, and we were able to degrade more of the pollutants in water. So this pushed us into our computational field. So we were now interested in looking at how can we design more materials that can become more efficient. So at that time, when we were looking at this project, perovskite type materials were the flavor of the month. So we decided, let's look into that. So in particular, we looked at strontium titanate, SrTiO3. So this is a promising material due to it being non-toxic. It has a high resistance against photocorrosion. It's low cost. It helps in the complete removal of contaminants. And it's also abundant. Its constituent elements are abundant. And it has high thermal and chemical stability. Where are perovskites used? In catalysis, ferroelectrics, oxygen transport, dielectric, and piezoelectric materials. So the most favored form of this particular perovskite is the cubic form because of high delocalization and longer lifetime of charge carriers. Unfortunately, it also has a limitation. So there's a snag. It has a very high band gap. In order for your material to absorb visible light, the band gap needs to be lower. So one way to do this is through electronic coupling of semiconductors. So the different methods of this electronic coupling includes semiconductor sensitization, staggered type 2 band alignment, Z-scheme, and phase junction. Of interest to this study of ours was the type 2 band alignment. Why? Because carrier lifetime is prolonged with an improvement in the interfacial charge transfer. So some of the results that we looked at that showed us that our coupled material actually followed a band 2 alignment. So the first thing that we looked at was band structure. This is important because you want to compare your pristine materials with the new materials that you have made. You want to see that the band gap actually has decreased so that your material can absorb in the visible region. So if you look at these diagrams, you can see we moved from high band gaps such as 3, 4, 3.5 to 1.6 and 1.7. So it has reduced significantly after the electronic coupling. Then we move on to partial density of states, PDOS. This is important information because you want to know which electrons are participating in this reaction. So PDOS actually shows you the electron density in the orbitals of the material. Another parameter that's quite important is work function. Work function tells you how easily an electron can be removed from the valence band into the conduction band. So the lower the value of the work function, the quicker or the easier an electron can move from one band to the next. And as you can see, if you compare the pristine to the heterostructures, the band gap, the work function has lowered significantly. To complement this, we did some calculations on the effective masses of charge carriers, which means the electrons and the holes. What is important here is the D value. So the D value is the ratio of the electrons to the holes. And the higher the D value, the lower the recombination rate and the greater the photocatalytic activity of your material. As you can see, it is the heterostructures that have the largest value. So it means that this material is highly active. Further information to confirm that this system is undergoing a band alignment was looking at the mechanism that was taking place and looking at the differences in values of the valence band and the conduction band. These values further confirmed that this particular or this new system is undergoing band 2 alignment. Lastly, under the water security topic, is we looked at the nature of pollutants, especially dyes, because we know the textile industry is the biggest culprits when it comes to dye pollution or organic pollution. So we specifically looked at dispersed dyes because these dyes have poor aqueous solubility. There are ways to enhance the solubility by making use of carrier or dispersing agents. However, this increases the cost and also it releases more toxic chemicals into the environment. And this is something that we don't want to do. We're trying to solve the problem, not create another problem. So what we decided to do, we said, okay, let's take the dye and put in some electron donating groups and electron withdrawing groups and see how that affects the solubility. Because we don't want to create unwanted dyes, and we want to improve the environment. So this, I've just got one slide on this because I went straight to the output results. So what we learned is that electron withdrawing groups actually support this dye to be more soluble. The placement of the electron withdrawing group is actually important because we actually substituted on what we note here as R1 and R3, and we realized the electron withdrawing group sitting on the R3 substituent actually promoted more aqueous solubility versus the one sitting on R1. So what conclusions could we draw from this particular study? 67% of the studied derivatives showed higher aqueous solubility compared to the parent dye. Cyano-derived derivatives was favored more over the NO2 group. However, when we had the CN and the NO2 group together with the amino group, we found it showed better solubility than if you would use substituted amino groups. And finally, the predicted solubility, the nature of the substituent and the position of the substituent was actually quite important. The second area that we're looking at is energy. Very important. Thermoelectrics. The definition of thermoelectrics is simply converting heat energy into electrical energy. So you know our current energy sources include solar, wind, geothermal, fossil fuels. These processes end up generating a lot of heat energy, which is wasted. So thermoelectrics looks into harnessing this heat energy into electrical energy. What is the advantages of this particular area? It's a greener form of chemistry, more sustainable form of energy, less maintenance to the process because now there's no mechanically driven process, and there's unlimited applications of thermoelectrics in fields such as your medical, automobiles, social, and so much more. However, again, there's a snag. Current thermoelectric materials have a figure of merit of 0.8. If we want that material to be very efficient, it should have a figure of merit of 1 and above. Ideally, you want your thermoelectric material to have a large electrical conductivity, but low thermal conductivity. So there are potential TE materials that include scutturidites, clathrates, 2D nanostructures such as transition metal chalcogenides, carbonaceous materials, and so forth. So we were interested in scutturidites, clathrates, and chalcogenides. These are the three superlattices that you see presented on the screen that we actually modeled as a thermoelectric material. So some of the data or some of the calculations that we ran were quite a bit. If you see on the left-hand side, we did band structure calculations, density of states, spin density of states, projected density of states, charge transfer, ionization energy and electron affinity, electric potentials, optical properties such as absorption, electrical conductivity, reflectivity, dielectric function, and phonon dispersion. As you can see, we also published a range of papers in this area. So when we compared our traditional thermoelectric materials to these superlattices, we found an improvement in the electronic and optical properties, as well as the charge generation and separation. And this is actually what we want. So what's the next step from here? We need to go into the lab environment. We need to synthesize these materials and test them to see how efficient they are. Finally, dreaded diseases, which is always on the table. Unfortunately, COVID we can consider as one of the dreaded diseases. And you can see computational played a vital role in getting vaccines out within a year or even less than a year. Because this is the methodology that you would follow in usual circumstances when you're in the lab environment. And if you look at these particular steps that you need to follow, yes, it will take you 15 to 20 years before you even get something out onto the market. But computational chemistry came to save the day. And we managed to get something out within a year. Typically, when we're doing molecular dynamics, we use a lock and key system. But now we know that not all proteins or drug targets are selective. So ligands can be flexible, and ligands bind to proteins, and the proteins can also change their conformation. So there are two methods or two ways in which you can approach molecular dynamics. One of them is structure-based design, where the protein target is known, and then you would do docking studies. The other method is ligand-based design. The target is not known in detail. So you make use of pharmacophores, you run simulations based on that, and then only can you do docking studies. So in our research group, and the study is ongoing, we focus on Alzheimer's disease. As you all know, this is a neurodegenerative disease. And it's also very difficult to diagnose this disease early on. And it's becoming a